Alright, so we're going to review these problems so that we can begin to make the connections between average atomic mass units, and this new standard of measurement we're calling the mole. We're asked to use dimensional analysis to determine the mass of a chlorine atom, knowing that 1 atomic mass unit equals 1.6606 times 10 to the negative 24th grams. Now, in order to be successful in solving this problem, we need to understand the implications of being asked to find the mass of a chlorine atom. Up to this point, we've understood that when we reach into a quote-unquote jar of atoms, we don't know what isotope we're going to pick. That's why we have our average atomic mass, that weighted average. So, our 1 chlorine atom's mass that we're going to use is going to be the average atomic mass of chlorine. So we need our periodic table to find that. It's always a good idea when doing dimensional analysis to ask what we're converting from and what we're converting to. If we're determining the mass, we're converting to grams. If we're going from the mass of a chlorine atom from the periodic table, those are in AMUs. So we're going from AMUs to grams. Do we have that conversion factor? We do. It's given to us in the problem. So, we know that 1 AMU is this, and that's our conversion factor. Therefore, we're going to take the 35.453 AMUs for chlorine and use that for our conversion. So we're converting 35.453 grams, not grams, AMUs for chlorine, 1 atom of chlorine, and converting that. We know in dimensional analysis our objective is to cancel out our units. So AMUs must go on the bottom. We know that the 1 is associated with our AMUs. That must go on the bottom. And that the 1.6606 times 10 to the negative 24 grams goes on top. That will successfully get us from AMUs to grams. Let's mark our sig figs. 1, 2, 3, 4, 5 sig figs here. 1, 2, 3, 4, 5. We'll end up with 5 sig figs. So all we're doing here is straight multiplication, an easy dimensional analysis problem. 35.453 times 1.6606. That gives me 58.8732 518 times 10 to the negative 24 grams of chlorine, or grams per chlorine atom is really what I should say. Now, we really should put this in proper scientific notation. So, I'm going to take this to the left one and make this larger. And we know it should be to 5 sig figs. So, 1, 2, 3, 4, 5. That's going to stay the same. 5.8873 times 10 to the negative 23 grams per chlorine atom. is our final answer. Knowing that conversion between AMUs and grams is nice, but it really isn't that helpful to a chemist who deals in quantities that are much, much, much larger. Oops, I wrote just 3. Let's fix that. That works in gram quantities that are much, much larger than to the negative 23rd, 10 to the negative 23rd. We don't have mass balances that can measure that. So we need to work with something bigger. The second problem is going to help us understand that. So we're going to actually end up using this quantity here. I'm going to take the unrounded version, copy it for our next problem. Put it down here. So for our next problem, it asked us to use dimensional analysis to calculate the mass of 6.022 times 10 to the 23rd chlorine atoms. Well, we obviously needed more to work with, which is why I carried this value over from the previous question. If we knew the mass of one chlorine atom, it's not a stretch to be able to go to 6.022 times 10 to the 23rd chlorine atoms in mass. Right? So the reason that I've carried over this value from before, because it's a conversion factor. I left out the grams per atom of chlorine. So that is our conversion factor. So what we're going from is atoms of chlorine, and what we're going to is mass of chlorine atoms. So we take our value that we're converting from, which is the amount of chlorine atoms, 6.022 times 10 to the 23rd chlorine atoms, times our conversion factor we obtained from the last problem. I left it unrounded because we never round until the end with sig figs. The chlorine atoms part is associated with 1, whereas the grams part, which is what we're converting to, is associated with the number that we obtained. And that had significant digits all the way to the 3. And we're using 4 sig figs for our number here. So our answer should have 4 sig figs. Units will cancel out, and we'll be left with our mass. And that was times 10 to the negative 24. Don't want to leave that off. I'm going to kind of see if I can move things around here without messing things up. Didn't think so. But I'm just erase this, since we already knew what we were doing. All right. Now I'm going to do my multiplication. 6.022 times 58.8732.518 gives me 354.53472233396 grams of chlorine. Now, forgetting it again, always checking yourself. It's important during these problems. Can't forget that we have exponents to deal with. So we have 23 plus negative 24. It's 23 minus 24, of course, which is going to give us our times 10 to the negative 1 grams of chlorine. Right? So, we know that this needs to go to 4 sig figs. And we need to round that 5. Oh, it's going to stay the same. 354.5 times 10 to the negative 1. And let's move our decimal point. Now, normally I would put this in proper scientific notation, but I'm not going to for a specific reason, and you'll see why in a moment. I'm just going to get rid of it and put it in an expanded notation, get rid of the exponent. So that means I'm just going to move the decimal over to one place, which will turn this into a 0, which just gets rid of it, right? So 35.4 grams of chlorine. And there's a reason I'm doing this. Now, let's go back and check something out. 6.022 times 10 to the 23rd chlorine atoms is what we wanted to find out the mass of. It's 35.4 grams. Compare it to our atomic mass. 35.4. It's the same. Same number we started our problem with, but in AMUs. Isn't it? Different number of sig figs. But interesting. Because the mole. 6.022 times 10 to the 23rd. This is the connection we want to make. Why? This number in atomic mass units can also be used as grams, because grams of this number equals moles of that many for that specific element. In other words, let me say it more clearly. If we use this as grams, that means that many grams of that element will always equal 6.022 times 10 to the 23rd atoms of that element. We call that the molar mass. Not only is this the atomic mass, it is also the molar mass. This number of that element, whatever it may be, always will be the gram amount that equals 6.022 times 10 to the 23rd atoms of that element. And this, that is more easy to work with in the lab to count atoms. We can deal with numbers of this size in the lab that allows us to convert more easily to atoms. So that standard number, 6.022 times 10 to the 23rd, equaling what we call a mole, bridges us between atoms of an element and grams of that element. That's why I call it the molar mass, because 1 mole of any element equals 6.022 times 10 to the 23rd atoms of that element, which equals this number of that element on the periodic table.